Okay, great. Good morning. As scientific disciplines advance and progress, they naturally become more mathematized. In particular, I like to think of mathematics as the operating system, the Mac OS or Windows of science and engineering. And today I'd like to give you an overview of some of the mathematics we've been using and developing to study our science, namely sea ice and its role in the climate system. And in particular, to me, one of the central challenges of sea ice science is how do you go from the micro, the finest scales, up to the macro, and mathematically use information on the smaller scales to derive and model behavior on macroscopic scales. So as a material, sea ice is a porous composite. When you freeze seawater, you can't incorporate the salt into the crystalline structure, and so you're left with these incredibly beautiful brine inclusions whose volume fraction, connectivity, and geometry depend strongly on temperature. And fluid flow through this porous microstructure governs very important processes in both polar climate and ecosystems that are hosted by sea ice. For example, the evolution of melt ponds on the surface, which determine the albedo of the ice, whether or not those ponds stay there or drain, that's determined by how easy it is for fluid to flow through this porous microstructure. And the robust microbial communities that live inside sea ice, their nutrient replenishment processes, as well as many other important biogeochemical processes, are controlled by the nature of this sub-millimeter scale microstructure. So that's only the finest scale. So from my perspective as a mathematician who works on composite materials, sea ice is a fascinating material in that it exhibits complex composite structure on length scales ranging over about 10 orders of magnitude. Starting with the sub-millimeter scale of the brine inclusions, the polycrystalline structure. These inclusions can join up to form large channels. The melt ponds on the surface of sea ice, I view this as a two-phase composite of ice and meltwater. The ice pack itself is a granular composite where the grains range in size from a few centimeters to 100 kilometers. And one of these central challenges in dealing with composites is how do you calculate, how do you mathematically predict the effective properties given information, some partial information about what's the geometry and the constituents on the smaller scale. And this is called homogenization. This is a whole field of mathematics and physics and engineering, where we might have information on the conductivity, say highly conducting inclusions like salty water in ice, and we have some information about the geometry, and then what is the effective conductivity? That's the homogenization problem, and then that's the forward problem, and then the inverse problem is, given both measurements, how do you figure out what was in the black box? What's the geometry in the mixture that is giving rise to that effective behavior? And these problems have a long and storied history, going back to Maxwell, Einstein. In fact, they were only able to work on the dilute suspension, get the first term in the Taylor series expansion in volume fraction. However, throughout the 20th century, there's been tremendous advances in the mathematical theory and the physics theory of composites, and this accounts for part of the very widespread use of composites throughout our world today. So what does this talk about? I'm going to give you a tour of recent results on how we are modeling macroscopic behavior in the sea ice system, but given that the title of this conference is Mathematics of Sea Ice, I'm going to have a specific focus on trying to tell you about some of the novel mathematical ideas and approaches that I think we're starting to use. So let's focus on the micro scale. So first, here's the brine phase in sea ice, and you see that as it's dramatically changes, the connectivity changes with temperature, no pathways, there's actually one pathway through here and many pathways. And actually there is what's called a percolation threshold. In other words, effectively, I view this as essentially an on-off switch for bulk fluid flow, where for brine volume fractions below about 5%, columnar sea ice is effectively impermeable to vertical fluid flow. But above that 5%, it's increasingly permeable. And with increasing temperature or brine volume fraction, that 5% percolation threshold for columnar sea ice happens by the Frankenstein-Garner relation, correspond to a critical temperature of -5 Celsius for a typical bulk salinity of 5 parts per thousand. And this is an example of a percolation threshold. So percolation theory is it was invented in 1958 originally to look at airflow through sandstones. And basically here's a square lattice. Only 1/3 of them are filled. Here, 2/3 of them are filled. And this is an impermeable state. There's no pathway, infinite pathway through this infinite lattice, but here there is. And the smallest P for which you have the appearance of an infinite cluster, that's called the percolation threshold. And it took quite a bit of, actually we have to use continuum percolation theory to get at this, and similarities with so-called compressed powders used in radar absorbing composites to actually derive theoretically that 5%. And it's become known, as you see here, as the rule of 5. So this percolation threshold, this critical point, plays a very big role in biological activity. Here's an algae bloom, and that cutoff, essentially, that's the percolation threshold when these algae that were growing through a convection-fueled algae bloom were cut off effectively from their nutrients. They're now in impermeable ice. Applying percolation theory to then actually predict the homogenized transport coefficient, namely the fluid permeability. So this goes back quite a ways. And so there's the 5%. There's the best known exponent for critical behavior of the fluid permeability in 3 dimensions. And this is not a fudge factor, but actually comes from a physics theory that's developed in hopping conduction and doped semiconductors to actually take this X-ray tomography data and look at the necks that control the bottlenecks for the flow. And we can actually calculate what that constant is in front from our X-ray tomography data in the so-called critical path analysis in semiconductor physics. And so actually, it took quite a while. I mean, this was originally conjectured, I think, in 1994 or something, of this rule of 5s, and it took a long time to actually develop the mathematics and the X-ray tomography methods to really see this, to really sort of confirm that this is actually what's going on. Now, this is all good and fine when there's no biology there. However, when there's algae in the ice, well, that kind of tends to mess up the transport of salt, the drainage of salt as it's forming, and you get more fractally type of inclusion. So I had one of my PhD students did a beautiful study of how EPS, which is secreted by these algae, extracellular polymeric substance, how did that affect fluid transport? In particular, the typical question is, how does the physics affect the biology? Here we're asking, how does the biology affect the physics? And so we developed a random pipe model, and whereas in biology-free sea ice, you get a classic log normal distribution for the cross-sections of the pore sizes. Now we found that you get through Jody Deming and Hayo Eichen and Christopher Krem's data, we find that you get a bimodal log normal distribution. And then my student Kyle Steffen was able to get some rigorous mathematical results to show that you get, in fact, a predicted drop in the permeability for this bimodal distribution. And we can actually then sort of really investigate this numerically, at least. Okay, now something very new. Back in, I think it was maybe 1993, I was sitting next to somebody in a celebrated research initiative on sea ice electromagnetics, and they were talking about the fractal nature of the brine and sea ice, that it kind of looked like fractals. And these were sea ice optics people. But to my knowledge, there's been no quantitative investigations of the fractal properties of the brine phase and sea ice. And so from our experience, you'll see later, from some of our experience with melt ponds, we've now looked at this finally and used some of this older X-ray tomography data. So I thought this would be appropriate. Here's England, looking at the fractal dimension of the coastline of England, and this is so-called box counting. Like how many boxes does it take to cover the boundary, and then as the boxes go to the size goes to 0, how many do you need? What's the exponent that describes that as a function of the size of the box? And so here's some of our our X-ray tomography data. And so we basically did this in 3 dimensions. We applied 3 different box counting methods to measure the fractal dimension of the brine phase and sea ice, and frankly, I couldn't believe what we found. This is the Sierpinski gasket, one of the most well-known exactly self-similar fractals. That blue line there is the curve that is a function of the fractal, of the measured fractal dimension of this as the porosity changes. The dots, the red dots, are our sea ice data for both granular and columnar sea ice. Seems to follow almost exactly this beautiful exact curve for this exact fractal. So this was really a surprise to me, and we're quite excited about this. And this actually goes back to Katz and Thompson, who discovered this blue curve, or something like it, with fudge factors in the context of sandstones, which are statistically self-similar porous media like sea ice. And also, long time ago, I've been showing this picture for a long time. That's a brine channel in sea ice. That's so-called diffusion limited aggregation. You got a particle at the origin, another one, Brownian motion, comes in, gloms on, and then more go, and this is what these kind of structures you get. So we actually developed a DLA, a diffusion limited aggregation model as well, which has this same kind of fractal behavior. And here's a really cool picture that we had commissioned to do, where we're looking at the implications of brine fractal geometry on sea ice ecology. So there's all these different scales. In other words, here's the largest scale down to the smallest scale, and then the smallest scale where all the biology is lived. So the brine inclusions are home to ice endemic organisms, bacteria, diatoms, flagellates, rotifers, nematodes, mydabbers, and nematologists. Very exciting for me. And the habitability and where they live is inextricably linked to this very complex fractal geometry. And in particular, in how critters are segregated, where they have to live, in terms of little necks and so on, and the sizes of the inclusions that they can live on and hide from each other and so on. So we're starting to kind of investigate these types of things. Okay, let's look at a little bit of the interaction. How do you start to sense all this, the interaction of electromagnetic waves with sea ice, but that also leads into some other interesting mathematics that we've used for other types of processes. So the basic remote sensing problem in sea ice is where we'd like to, say, calculate the effective electromagnetic properties, like the effective complex permittivity, and then there's the inverse problem of inverting for all that. And so the underlying formulation is the quasi-static Maxwell's equations, as shown here. And what we're interested in is the effective complex permittivity, which is a complicated function of the ratio of the complex permittivity. So these are complex numbers, as well as the composite geometry. That's really what's determining things. And then one of the key ideas that actually goes back to my PhD thesis was this so-called Stieltjes integral representation. So these are a very important class of functions for which you have these beautiful integral representations. And what's so striking about this is all the material parameters are in that complex variable, but what makes the whole problem go is so-called spectral measure. So this is like mu of z dz. It's what you're integrating against. However, it's a little more complicated than that. It's actually a spectral measure of a self-adjoint operator gamma chi, where gamma is projection onto Courant-free fields, and chi, that's where the randomness, that's where all the information about the brine comes in, and where the mass is the volume fraction of this measure. And what mathematically makes this whole structure go is to manipulate the Maxwell equations into the so-called resolvent form for the field, for the electric field. And that will be the same thing in many other problems where we can extend this type of these ideas. And so this operator gamma chi takes us from the micro scale to the macro scale. And this representation then distills the complexities of the mixture geometry into the spectral properties of an operator, very similar to the Hamiltonian in quantum physics. One of the main uses of these powerful integral representations is to get literally rigorous bounds, rigorous information. You don't know exactly what's in the material, but to get rigorous bounds on the homogenized or effective property. These are complex permittivity results here. We've done inverting for the connectivity of the brine inclusions and so on from bulk measurements, as well as a number of other results here. So now, but sea ice is also on a larger scale a polycrystalline material. And so we can homogenize that. That's a different problem. Nevertheless, we're able to manipulate the equations into the exact same form. And so we've developed a Stieltjes integral representation for the effective complex permittivity of any sort of polycrystalline material. This is not just sea ice. This is math again. This is glaciers, whatever, rocks, and so on. We've got forward and inverse bounds, and we've applied that to using a two-scale homogenization because each crystal is a composite itself with the brine inclusion. And we've developed an inverse bounds to give methods for distinguishing ice types. That's one of the things we're most interested in, is distinguishing between granular ice and columnar ice. Why? Because they have such different percolation thresholds, which is biogeochemically and biologically very important. My first published work with Steve Ackley, long time ago in 1981, was to look at anisotropy within the horizontal plane when you have aligned sea ice. And now with one of my amazing freshman researchers back at the University of Utah, we've done this all rigorously, gone back and applied these integral representations in the polycrystalline case, but developed it in the anisotropic situation to compare. Another large program that we have going on is advection diffusion equations. Nutrient and salt transport in sea ice, heat transport in ice, thermal conduction, but with convection. Ice flows, they undergo Brownian motion, but they're being advected around. These are all advection diffusion problems. Here's the advection diffusion equation for a divergence-free field, incompressible. That's the homogenized heat equation with an effective diffusivity. And then there's Andy Maida and Marco Avellaneda took our functional analytic framework that I did with back in the early 80s and adapted that to the advection diffusion problem. And then maybe about 10 years ago, we started taking that a lot further and developing new forms of these integral representations and then applying the thermal conductivity problems and other types of problems in the sea ice world. This is just to show some of my pictures of tracers, some of my tracers that I put in, and beet juice and all kinds of stuff that I like to put in ice to see what's going on and watch the flows and so on. Another major problem was sort of a tour de force pushed through by another PhD student, Christian Sampson, who's now at NCAR, to actually develop Stieltjes integral representations and rigorous bounds for the complex viscoelasticity of the ice-ocean layer, treated as a two-phase composite of ocean and ice. And this is the first theory of this key parameter in wave-ice interactions that was only fitted to wave data before. What's particularly fun for me is my mathematical grandfather, Joe Keller, was the first to sort of do some of the mathematical modeling of this many years ago. Okay, but it's this spectral measure, it's this thing that you integrate against that has all the geometry that makes the whole problem go. So it depends on the composite geometry, only on the composite geometry. If you have a microstructural image, then it gives a binary network, like a random resistor network, and then that fundamental operator, that gamma chi, becomes what's called a random matrix, a matrix with complex random entries. But then we can actually compute the spectral measure from the eigenvalues and eigenvectors from that random matrix. There are other fancier ways of computing it, but it turns out by doing it sort of the really kind of dumb, straightforward way, by looking at the matrix and computing, we can actually then do statistics, which opened up a whole new world for us. Namely, here's the ice pack, and here's the spectral measure. We get here's the water phase, the ocean, non-percolating, just starting to percolate. It percolates, you get a pole at the origin. But here's what's so fascinating to us, and we just didn't expect. This is so-called eigenvalue spacing distributions. How far are the eigenvalues spaced? So when the ocean phase here is not percolating, they're completely uncorrelated. They don't talk to each other. However, as you start to develop long-range order in the system, well, you get a transition from uncorrelated plus undistributed eigenvalue spacings to a so-called universal Wigner-Dyson distribution, which comes up in random matrix theory. It comes up in the zeros of the Riemann zeta function, the most currently storied unsolved problem in pure mathematics. But it turns out that's just a glimpse of a larger picture that we discovered, namely that the connections to Anderson transitions and localization in wave physics, where basically you get essentially either extended states or localized, and this is at the heart of semiconductor physics and transport in disordered media. And however, there's no waves here. This is wave physics, but we have no wave, but we get all the same underlying mathematics and physics. So in other words, we found an Anderson transition for classical transport and composite, and it all came from our spawn by our investigations of the spectral measures and their statistics of the eigenvalues and eigenvectors for brine, melt pond, and ice flows. And we see these universal eigenvalue statistics, extended states, Anderson localization, mobility edges, just like in solid state physics, but it's not solid state physics. One interesting thing this led to was a spin-off to high-tech composites. one of my PhD students, David Morrison, whose dad is Jamie Morrison, who's a famous physical oceanographer I went to Antarctica with. That's how I knew him. So we did a PhD, he did a PhD with me, and he developed these amazing moire composites, sort of tunable quasi-periodic composites that have exotic properties. He just published this a little while ago in Communications Physics. It's like you twist one lattice relative to the other only by 2 degrees, and you go from completely periodic bands and gaps to almost like random percolation type of behavior. Turns out in the review process, somebody pointed out this was almost exactly like twisted bilayer graphene, where there's Nobel Prizes won for this stuff, and you have the same kinds of interesting behavior. It's just fascinating. And again, where did this come from? By studying sea ice. And it's mathematics. Okay, so we've also been, as I mentioned before, we've been studying melt ponds a lot, and we asked the first question. I looked at that, said, hey, that's a fractal. Let's look at the fractals. I thought there'd be a fractal dimension. Turns out there is a, well, let's see, so just a reminder of the fractal of simple curves, simple Euclidean curve, the Koch snowflake, fractal dimension 1.26. This is the maximal fractal dimension you can get in 2 dimensions, is 2, a so-called space-filling curve. And so instead of 1 fractal dimension, we found a transition in the fractal dimension, as you can see here, centered around 100 square meters. A simple pond, starting a transitional pond, and a highly complex self-similar pond with a boundary that's behaving like a space-filling curve. So one of my, again, starting in Calc, I'm teaching Calc 3 right now, and one of my Calc 3 students from a number of years ago, he developed this method here where we have a random surface, and then we just look at the level sets. This is a perfect calculus. That's what we're doing in Calculus 3 literally right now. In fact, they had their first exam today. So good luck, everybody. You have a plane up and down, start at low, and then you start to rise up, and they actually look like melt ponds. But this model I learned from Isachenko, who's a plasma physicist. So we took that and applied that to melt ponds. And from the statistical properties defining the random surface, we are able to study the nature of the fractal transition. But we've asked the question, from our perspective, nobody's really understood exactly how does this fractal transition arise? There have been several models, including some of ours, that replicate the transition in the fractal dimension, but none really explain mechanistically what's happening. What is it about melt ponds that do this? So we've used Morse theory, which I'll just mention, I'll just show you one picture about that, applied to this random surface model to show that it's the saddle points, the saddles, which is where the water level that's where things complexify, and we can prove using Morse theory and percolation theory, these are the only places where the actual topology can change that affects the overall connectivity. In fact, we've combined rigorous lattice and continuum percolation theory along with this Morse theory and differential topology to prove some of these various results. But the key result, the key thing that, again, is these saddles. And Morse theory, this is actually out of Wikipedia, Morse theory is all about tell us that changes in the topology of a surface, namely, you take a slice here, you just get 1 connected region. You take a slice here, you get 2 connected regions. Where does the change happen? Right at that saddle point. So Morse theory tells us that changes in the topology of a surface occur at critical points of smooth functions on the surface, such as the height level, that's a smooth function. It can only occur at the maximum, minimum saddles, but it's really the saddles that we are, in fact, most interested in. And one of the main results, what then explains the transition in the fractal dimension, is we looked at the isoparametric quotient, namely the perimeter squared over 4 pi times the area. And what we found is at these saddle points, when 2 ponds turn into a much more complex 1 pond, you get these jumps. It sort of jumps up in the isoparametric quotient. And that's ultimately what's driving this transition in the fractal dimension. And also these saddles play the critical role in horizontal transport of fluid and drainage of fluid through seal holes and places like that. Like my friend Hayo and his colleagues staring at this drainage vortex, which is like, of course, if you slip, that's kind of the end, I think. You ain't coming back out of that hole. Anyway, melt pond connectivity enables vast expanses of meltwater to drain down these seal holes, thaw holes, and leads in the ice. So that's, in other words, and it's the saddles that control. In other words, I'm connecting this up with all this semiconductor physics as well, and it's these saddle points that control the scaling of the horizontal fluid permeability. Okay, They're really interesting. Again, just like we stumbled into random matrix theory through analysis of these spectral measures, we've also now stumbled into topological data analysis and so-called persistent homology. So the Euler characteristic is a fascinating quantity associated with a surface, a topological invariant, the number of maxima plus minima minus the number of saddles. And then there's a so-called filtration, a sequence of what are called nested topological spaces, and that's all that is the water level. You get a nested sequence of these surfaces. And instead of the Euler characteristic of one of those surfaces is not so interesting. What's interesting is how that changes when you start below the surface. You just hit a bunch of minima, and then you start to get more saddles. And so this is this so-called Euler characteristic. And what is amazing, when we average it and do all finally the right things, the zero of the Euler characteristic corresponds exactly to the continuum percolation threshold. And this has also been found in other porous media literature. So we're really fascinated by this. And there's some of these melt pond donuts, because these actually take place on a torus, so they're really tasty. I think Ivan Sudakov will talk about another really interesting model where we developed where we used a 100-year-old model called the easing model for magnetic materials to explain melt pond geometry, where we have spin up and spin down. And here are some of our model results, where we just minimize the energy of the easing model. And here's the real melt pond. And then the last thing I just want to mention is sort of again the connection with the biology. Okay? And these melt ponds, of course, act as windows, allowing light into the upper ocean. And there's fascinating questions about sub-ice phytoplankton blooms, and also how does the geometry, not just the area fraction of the ponds, but the geometry affect the distribution of solar energy. This is led by Chris Horvath, who's here. So in this vein, then, in closing the loop, then, going back to the microalgae or the algae in the microstructure, here they are. They comprise about 80% of a polar bear's diet, as you can trace this back. And this is Jody Reimer, who's now assistant professor in math and biology at Utah, who's really led all this. So the question is, can we improve agreement between ice algae models and data? We start with the simplest possible algae bloom model, input, uptake, and loss, the algae and the nutrients, and so on. However, there's poor agreement with the data, poor agreement between models. This is the bloom, that's the nutrients. But there's incredible heterogeneity. This is going back to Klaus Meiner's incredible heterogeneity over many orders of magnitude, just on the meter scale. So if you really need to treat the parameters, the growth and other parameters in the simple model as random variables according to a distribution. But however, the problem is it would take like 8 hours just for one run. You need like 10,000 runs or something. This ain't happening. So we've introduced modern uncertainty quantification methods for ecological models. We just published this a couple weeks ago in Ecology Letters. And the idea is and this is again new mathematics that we're introducing, so-called polynomial chaos expansions. It's effectively like a separation of variables, a separation in time and the random variables. And then ultimately, the point is that we seem to, in other words, if you do it this way, you can really do it, and you see that you get incredible differences. There's the deterministic, which is what's kind of being used. But here's what's actually going on. In other words, the peak bloom is half what you would measure doing, just without treating it as random variables. So last thing then. There's a nice article we had in the notices of the American Mathematical Society. A number of the people in this room were co-authors. And then finally, I want to mention, this is sort of an advertisement. We have a lot of open positions in mathematics of sea ice and climate at the University of Utah. We just got a very large grant from the National Science Foundation. We have other grants as well for PhD and graduate students, for postdoctoral fellows, instructorships, and even tenure track in mathematics and materials. Please contact me if you have great students, graduate students, postdocs, and so on connected to this. And thanks to ONR and NSF for supporting all this research. So thanks very much.
Okay, thank you. Bruno.
I'm really curious about your fractal analysis, because we do this also like in the CIs, like a scaling in CIs, the deformation. So do you do like a threshold method where it's a 0 or a 1 and basically...
yeah, that had to be done like yes.
That's the way you do it?
Yes.
Okay, so yeah, I would love to speak to you. I'll present something along those lines. We do it differently, and I think there's issues with the way we're doing it, and I would love to hear like your thoughts.
Because it took quite a bit. In other words, we've done it so many different ways, you know. And then ultimately there was some other software that we found and some other methods that, you know, we're cross-checking constantly to make sure everything looks right. I mean, it was getting these fractal dimensions right. I mean, part of, you know, like for example, if you're looking at the fractal dimension of something in 2 dimensions, you get an answer from some distribution, you get an answer of 4. Well, that's not right. You know, in other words, there's ways of telling, and there are ways of, you know, in other words, the maximum fractal dimension in two dimensions has to be 2. In 3 dimensions, it's going to be 3. And so if you're getting numbers that are not making any sense, you know, anyway, so these are interesting technical issues, though.
Well, the mic's right here. Can I really enjoy the talk? A quick question also about the fractal dimension. So you said that when you looked at that picture of the melt ponds, it looked very fractal to you, but I need to sort of refresh and don't really remember box counting dimensions, but it looks like if you just had a box counting dimension of 1 and then a transition to 2, isn't that not like a regular fractal that has a non-integer dimension?
No, right, sure. In other words,
are you basically showing us the
fractal behavior? Sure.
The melt ponds don't have fine structure in some funky way like fractals,
but
they're not fractal.
What's happening is in other words, one way of viewing the fractal dimension, it's the perimeter compared to the area. When you start, in other words, as things grow and you're dramatically you're getting so much perimeter compared to the area as you grow, that's fractal behavior. That's what it is essentially. But
it's settling on this value of 2 when you get in that figure
right.
No,
yeah, exactly. That's because that is certainly the maximum value. I mean, we don't know if it really hits 2, of course, but you know that is the maximum value mathematically that you could have in 2 dimensions for a fractal curve. Is, you know, a space-filling curve is the maximum is 2, and that's what we're sort of, you know, it's starting to behave like that because you're getting so much perimeter compared to area. That's your question?
Maybe I might ask you more. Does that imply that there's not much structure on fine scales?
Oh, sure.
Like your classic fractal that you build.
Down this, you know, it doesn't. It's infinity. You go either way, down, you know, epsilon to 0 or n to infinity. Either way, it's fine.
Well,
it's equivalent mathematically.
Okay, there is another question. As well.
Okay.
Okay, so
okay. I could probably comment upon what. Yeah. It's yeah. But let's keep this. Okay, I'll keep this really short then, because I think Ian's already hogged a lot of time. I guess I was just going to say I was really struck by the fractal dimension of the brine channel, brine structure.
Me too. We did
not
expect it. Let me just say one thing. Okay, when we did it in temperature, it's like, oh, that's cool. You can sort of see something, but it was. I said, hey, Nash, this is a guy that started with me in Calc 1. Anyway, it's amazing. I said, oh, let's look at. Why don't you make the x-axis porosity, brine? And then it was like, wow. It was clear that something interesting happened.
Well, I'll leave it there, but just to mention that there is actually a statue of the Sierpinski gasket outside this building.
Really?
Okay. So if you want to see what Ken's been going on about, okay, there's a statue of the Sierpinski gasket outside.
Thanks.
Okay,
Thanks.
well, took me a while to get the microphone.
Hello, thank you for the talk. It's just a small question because you talk about the importance of porosity into porosity measurements into sea ice for the drainage of the melting pond, I think.
Yes.
But as in rocks, it will be mostly the faults that will be important for such a phenomenon more than
I didn't understand that.
The question is, what is the because we know that sea ice got faults because of breakage, and isn't the faults that appear into sea ice that will be predominant for the drainage of melting pond over the pure porosity of the material?
The relative contributions of those two processes that you're talking about, I'm not sure what but certainly without a doubt. I mean, the drainage through the port. I would think that what you're saying is probably true. In other words, you've got a big hole, but it's highly heterogeneous. In other words, okay, here's an area. There's not a lot of big cracks. It's just nice homogeneous ice, but you're getting drainage. Okay. Anyway, so I think that trying to quantify the relative, again, contributions of these different kinds of, in terms of drainage processes, is an interesting question. I don't necessarily know.
Very, very quickly, there is a Zoom question.
Okay.
So have you looked at how microstructure of the interface plate spacing affects the magnitude of the percolation threshold?
Plate spacing in the micro plates of the.
Well, I'm reading that. That's.
I think the answer is no.
Okay. So, okay, she said yes. Yes. Thank you. Okay. So I guess we can go to our next speaker. Thank you, Ken, for your talk.